So this is where the nanotechnology and the nanowires come into rescue. So the benefits of nanoscale are the use of nanowires in phase change memory includes in a smaller cell volume. If you look at the 2D thin film PRAM at the bottom of the slide, so you have an electrode at the bottom, which is the yellow color, and then there is an electrode at the top, which is the red color, and the light blue color is the phase change material. The entire light blue color phase change material does not undergo the phase change between amorphous and crystalline. It is a small dark blue region which looks like a little mushroom. That is the volume that undergoes phase change. And now if you were to use a nanowire, then the cell volume is even smaller, which means your thermal budget to drive the change back and forth between the two phases, that thermal budget is going to go down, which means the programming current can be smaller. So that is one advantage. The second advantage involves the reduction in melting point when you go from bulk scale to nanoscale. So that also helps to manage the thermal budget, reduce thermal conductivity, large aspect ratio nanowires, and perfect surface morphology. So these are all the benefits. I mentioned that the nanowires exhibit a melting point which is lower than the corresponding bulk value. What is melting point? It is a transition from solid to liquid. So the solids have a diffraction pattern. When it becomes a liquid, the diffraction pattern disappears. So in this case, the nanowires were placed inside a transmission electron microscope and they were heated. The diffraction pattern was continuously monitored. At the moment when the diffraction pattern disappears, that actually is defined as the beginning of the melting. So that's how the melting point is determined. On the left side of the image that you see a single nanowire with its diffraction pattern, and then once it starts, the right image shows that the nanowire begins to melt and start to actually ooze out. This is a case of germanium telluride nanowire. The germanium telluride nanowire, after it is grown and when it is brought to the TEM room, it already has a native oxide, germanium oxide. The germanium oxide melting point is very, very high. So it doesn't melt at this temperature around 400 degrees. It's only the germanium telluride that melts and oozes out of the germanium oxide shell. This experiment allowed to measure the melting point of nanowires very accurately. The germanium telluride 70 nanometer wire, the bulk melting point is 725 degrees centigrade, whereas the 70 nanometer wire melted at approximately 390 degrees centigrade. So that's close to 50% reduction. Likewise, indium selenide nanowire, the bulk melting point is 890 degrees centigrade, and the nanowire, 40 nanometer diameter nanowire, melted at 680 degrees centigrade. So that's close to about 25% reduction. So this melting point reduction is a function of diameter. So if you make nanowires even thinner, as less than 70 or less than 40, then the melting point reduction would be even larger. So it's a diameter dependent property. A rudimentary indium selenide nanowire memory was constructed, and so here I'm showing the switching behavior of this indium selenide nanowire memory. The image on the left shows the resistance of the nanowire, and then the x-axis is the reset voltage. So up to the application of about 5 volts, the resistance remains low, and then after that, after about 5 volts or so, the resistance becomes very quite high, and that is called the reset operation. Then in the set operation, the reverse thing is shown on the image on the right side. So this image shows repeated set reset cycles going from low resistance state to high resistance state, showing about 20 cycles or so. This table compares indium selenide nanowire PRAM performance with the corresponding indium selenide thin film based PRAM. The punchline here, or the key point here, is when you use indium selenide in the form of a thin film, the programming current, which is a critical parameter, the programming current required was approximately 0.4 milliamp or 400 microamp. Whereas when you use indium selenide in the nanowire form, the programming current goes down to as small as 11 microamp. So the projection now is it's possible to make nanowires as small as about 10 nanometer diameter and then achieve programming current as low as like 1 microamp or even smaller. So the next set of applications I'm going to focus on includes optoelectronic devices, for example, nanoscale lasers. The nanowire diameter can be smaller than the emission wavelength in vacuum, and you can make the length as long as a few tenths of microns. So this allows you to make very small lasers. The optical cavity formation is due to the difference in the refractive index between the nanowire and its surrounding. So you make the difference larger, then it's possible to achieve stronger mode confinement. There are other advantages of the nanowires and lasers. First of all, you can get cylindrical geometry. I mentioned several times the nanowires grown using the vapor liquid solid technique. They have very high quality crystal structure. Then you can also get two-dimensional arrays of lasers using vertical nanowire arrays. So far, the lasers investigated in the literature include zinc oxide and wide band gap material like gallium nitride, the indium nitride, and a variety of other materials. So this image shows the very first infrared single nanowire laser using gallium antimonide nanowire, which is useful in the telecommunication band of approximately 1.5 micron. The next set of applications include photodetectors, photoconductors, and photodiodes. They produce an electrical output signal in response to an optical input signal. The photoconductors use a thin film, or you can use a nanowire form of the semiconductor. Essentially, whether you use a thin film or nanowire doesn't matter. Both of them are contacted by a pair of electrodes. The photodiodes, in contrast, they consist of a p-n junction. So when you have an optical input that produces electron hole pairs near the junction, where there is a high field, and the carriers get swept away or collected towards the appropriate electrodes. So you can get fast response time and very high sensitivity and high signal to noise ratio compared to the photoconductors. So here I'm talking about cadmium sulfide nanowire photoconductor. If you look at the picture, you can see an image of a nanowire which is cadmium sulfide nanowire in a two-terminal configuration. So you have a pair of electrodes, and it is done on highly doped silicon wafer with 400 nanometer silicon dioxide. The two electrodes are titanium and gold electrodes. You can fabricate them using e-beam lithography and an evaporation followed by liftoff. So in this particular case, a frequency doubled titanium sapphire laser was used, and the optical excitation was 1 kilohertz. The photoconducting characteristics at 400 nanometers were monitored. Approximate power was 0.7 watts per centimeter squared. So the photoconducting current is about 100 times larger than the dark current. And the shape of the curve, it looks very familiar, like a metal semiconducting junction with back-to-back Schottky contacts between titanium and cadmium sulfide. The next one is a gallium nitride nanowire-based LED. In this case, the gallium nitride structure is grown and a p-n junction was created within the same nanowire. So first you start growing gallium nitride nanowire using vapor liquid solid technique, and the as-grown nanowires are n-type doping, and so this was using gallium chloride and ammonia system, approximately around 400 plus degrees centigrade. And then after a certain point you start introducing magnesium vapor, and the magnesium vapor it provides p-type doping. So this is how that you create a p-n junction. And it's possible to get a reasonably abrupt junction here. And if you want that, you can control the growth time and then the gas flow of magnesium in order to get a graded junction as well. Okay? So the LED fabrication involved preparation of contacts using e-beam evaporation followed by annealing. So at forward bias, the p-n junction produces very high emission, and the emission peak occurs approximately at 3.2 eV. Light emitting diodes, obviously they have applications in lighting and displays. Conventional LEDs are planar. They do have some drawbacks, kind of poor light extraction. The spectral width is pretty wide. The output tends to diverge a lot. So people started making micron size LEDs. They generally offer better efficiency, but there are some issues with that as well. In order to make the LEDs, dry etching is a critical process that has its own limitations, particularly leaving very poor surface, and that could have traps. So that's an issue. Other issue is epitaxially grown layers. You have to make sure that you have a good lattice match with the substrate itself. If there is any significant mismatch at all, that will lead to all kinds of dislocations. Those dislocations can act as a non-radiative trap centers, and that will adversely affect the performance. But lattice mismatch is not a serious issue when you have nanowires, because the area is much smaller. So the LEDs that have been demonstrated by the research community so far include gallium nitride, indium phosphide, and zinc oxide. Just to summarize, a variety of nanowires have been grown. These are elemental materials such as silicon and germanium, a number of different oxides and nitrides, 3,5 materials like gallium arsenide, indium phosphide, 2,6 materials of various antimonides. All of these have been grown to date using vapor liquid solid technique, and a few other approaches too. The VLS approach is more CVD-like, and in that sense, it's amenable for integration in a device fabrication scheme. Inorganic nanowires, they have been investigated for a variety of applications, including electronic devices, optoelectronic devices such as lasers, LEDs, and photodetectors, sensors, field emission devices, thermoelectric power generation, and piezoelectric power generation, and many others. So the preliminary results that we have seen so far, they tell us that the nanowires can provide a competitive avenue for many of these applications, competing with materials like carbon nanotube and graphene. Some other remaining challenges include the need to control the diameter precisely, and also this kind of control and growth over large wafer surfaces such as 200 millimeter or 300 millimeter wafer. If we end up doing ternary compounds, for example aluminum gallium arsenide, then the need to control the alloy composition. One of the key challenges is to develop the ability to grow these nanowires at low temperatures, because if you end up using catalysts such as gold, then the growth temperature is about 700-800 degrees centigrade. That precludes the possibility of using many types of photoresists, and it's also very hard to integrate that kind of high temperature growth in a device fabrication scheme, particularly if you need to do pattern growth. So it would be ideal if the growth could be accomplished at temperatures as low as 150 or 200 degrees centigrade. So the low temperature growth processes, and of course we have to continue to develop applications and device processing, and we have to pay attention to yield, particularly when we talk about wafer scale fabrication.